let's say that we have a signal that looks like this. And let's say that thing is called u of t, or let's say that's called y of t. And after we have sampled that signal, the notation that we will use to indicate that we have sampled the signal is to have a star. And what I'm going to draw for you now, I want everybody to be incredibly clear that this is not mapping to any real form of reality at all in any way. There's no sense of wires being involved in actually having this kind of signal, but the mathematical game that we play is that we pretend that what the sampler does is it closes at exactly those moments in time, but it produces an impulse, a Dirac delta, at every sampling moment. Right, so if this thing is closing with a frequency or at a period of delta t, a sampling rate of delta t, what we imagine is that at every one of those delta t moments, there is a Dirac delta. Now, I hope everybody understands why I'm saying that that could not actually be the way that it works in wires. Is everybody following me about this idea? Even if I did that, I wouldn't have that, right? Like if I just like opened and closed the switch, if there were some kind of a signal flowing in this wire of some kind, or if that were a circuit, and I closed that switch, what would actually happen is what I would capture would be, are you guys not, okay, let me take that a little bit back, right? So if I were doing this, if I were just closing that switch, does everybody understand that even if I just like closed my eyes and then looked at it and closed my eyes and looked at it, the thing that I would have in my mind, the thing that I would write in my book would be the values, right? So I'd have 0, I'd have delta t, I'd have 2 delta t, 3 delta t, and so on in my time column. And in my value column, in my y column, I would have the value that I had observed at that moment in time. And so maybe if that thing started at time 0, maybe the value would be 0. If after delta t seconds, let's imagine that's 1. Let's say after delta t seconds, it's about 0.4. Let's say after 2 delta t seconds, it's about 0.83 or whatever, right? And so those are the values that I would have ended up writing down. And I want you to understand that those values, or that list of values, is not a Dirac delta. It is just a number written down on a piece of paper. That is what we have when we have sampled a continuous signal. We have the values of the signal at the sampling moments. So why do we take the time to write this thing down? Because the whole idea of this pulse train sampler, so this thing over here, you can represent mathematically as the sum of all of these Dirac deltas shifted by a certain amount of time to the right. Okay, so that's what a Dirac delta by itself looks like. If I shift that, if I just wrote that down, I would have just an infinite array of Dirac deltas, but just shifted up and up and up, right? So I'd have an infinite number of them, but they'd all be conceptually the same size. Now the mathematical, this is like the mathematical fiction that we're doing, is we're saying, well, I can encode the value of the function by kind of having the function evaluated at n delta t as the coefficient of that delta. Right, so this is the formula that we come up with, and we say, well, this is, that's the formula for f star of t. And the idea is that we would take this kind of, that the sampler introduces this new kind of signal. But I want you to very clearly understand, this does not exist anywhere in the world, right? This exists only for our mathematical benefit. It exists because it has an easy Laplace transform. Does everybody understand why that function would have an easy Laplace transform? Let me remind you, back in the table, right? So in the table we have f of t, we have Laplace of f of t. So when I say the table here, I'm talking about the data sheet, which I'm starting to realize you guys basically never use, but which I have asked you to commit to memory at least the first 3 lines. Now let's all together write down the first 3 lines of the data sheet, right? The first 3 lines of the data sheet says if f of t is one of these guys, then the Laplace transform is 1. Okay? So why do I say that this thing at the top right there has an easy Laplace transform? Firstly, it's a sum. Okay? So the infinite sum shouldn't bother you because the Laplace transform is a linear transform and it can kind of just go over sums, right? So because it is a linear transform, the Laplace transform of a sum is just the sum of the Laplace transforms. So that by itself shouldn't scare us, right? And so let me just explain what I'm trying to do. I'm trying to do the math that is equivalent to the math that we did for continuous systems on discrete systems. And that math involved taking the Laplace transform of the input signal, taking the Laplace transform of the system, multiplying the two in Laplace, and then taking the inverse Laplace to get back to the real system. And so I'm hoping that there's something similar for these discrete systems. And this is the first step on that route, is to express the sampled signal in a way that is mathematically convenient to allow Laplace transformation. Right? So because we have this thing over here, because we have this easy thing over here, if I was trying to get the Laplace transform of, now this is not a table, this is a continuation of this. If I were trying to calculate the Laplace transform of that, remember I would take the Laplace transform of the sum of that thing, which we've just said is equal to the sum of the Laplace transform of the thing, which is delta t minus n delta t f in delta t. Okay, so that first step is easy. And now you're saying, but wait a minute, Cole, this is weird because there's a product. And I know that, Laplace transforms of products, there's no nice rule for me to do Laplace transforms of products. But I want to remind you that this thing over here is a constant. It is a number. It's one of these things that we wrote down over here. In other words, by the time that we do this Laplace transform, this is not a function of time. These are the values of the function at those times, which is a very different thing. Okay? And so actually what we just have is a lot of Dirac deltas with a coefficient which is known by the time that we evaluate the Laplace transform. So it's just a constant value. Okay? And so in the same way, again, because we have a linear transform, I can actually do this. Right? So let me just draw that properly. Okay, because it's a linear transform, that constant moves out of the Laplace, because a constant times the Laplace of something is the same as the Laplace of a constant times something. And so now we just have this problem of what is the Laplace transform of a shifted delta. We know that the Laplace transform of the delta itself is 1, and we also know what the shifting formula is. Right? You've encountered this before when we did dead time. And so very clearly we end up with 1, right, which is the Laplace transform of the delta, times e to the minus n delta t s, which is the shifting formula, right, times f of n delta t. Okay, and so this is the Laplace transform of a sampled signal. So if I have an original signal f of time and I sample it, well, the first thing is obviously I can calculate the Laplace transform of the original signal, right? So I can calculate this Laplace transform, no problem. And I've now shown you that I can actually calculate the Laplace transform of this thing as well. Also, no problem. Okay, as long as I do a little bit of mathematical magic. Now, at this point, we're going to introduce and there's a couple of ways to think about the Z transform, but this is the way in the textbook. I'm going to take a whole different take in a couple of seconds, but this is the complete set of what the textbook does. Is it says basically, well, it looks like when we're working with sampled signals, we're going to have a lot of terms of that form, right? In fact, some may say an infinite number of terms of that form, but we're going to have lots of terms of this form, okay? And we're going to get tired of writing e to the minus delta t s at some point. And so instead, we're just going to say, let's call z. Let's define this thing called z. And we're going to call z e to the s delta t. And how that simplifies our calculations is that it moves this into and at this point we have what is called the Z transform of the signal, of the sampled signal. Okay, so we would also say that that is the Z transform of f star of t. And I think the most confusing thing about the Z transform is not this math, because the math actually is pretty simple. I think the most confusing thing about the Z transform is how the notation is abused in such a way so that you can't think of the Z transform as having one single definition easily. In other words, you will see that Z being taken of, and so here is something you've never seen, right? You've never seen somebody take the Laplace transform of a transfer function. Does that even make sense? So if I say so just this is an aside, right? Like if I say, what is the Laplace transform of 1 over s plus 1? Right? Would that even make sense? No. Why? Because you can only take the Laplace transforms of things in time, right? And so Laplace transform takes things that started in time and gives you things that ended in the Laplace domain. Okay, so this you would be right to be confused, because what exactly does this mean? Unfortunately, you will see lots of different things inside of a Z transform notation like this. So things that you will see are the Z transform of f of t. You will see the Z transform of g of s in the textbook. You won't see me use that notation much because I hate it, but I'll explain to you what the textbook means when they do that. You'll see this thing over here, which I regard as kind of the definition of the Laplace transform of a sampled signal. And you will also, like if you search Wikipedia or if you search on the internet, you will find pretty much none of the definitions that we talk about in the textbook, but what you will find is the idea that the Z transform of a sampled signal is equal to this infinite sum like this. And so you see that there's, on the screen here, there's tons of weird stuff happening, right? How can it be that I can do the same operation on variously a sampled function, a continuous function, and a Laplace transform? Now the answer is really simple but super confusing. What makes it easy to understand is the need, the thing that people are trying to express when they do a Z transform is they're trying to say that they are wanting to end up with a series, a polynomial in Z. And in most cases, what they're implying is that they have something that used to be in the continuous domain, and they are trying to get it into the discrete domain. And so this is why this notation feels natural to somebody like Seaborg in the book, where they will say, oh, well, we just get the Z transform of the transfer function. And like if you're like me, you read that and you're like, wait a minute, but that doesn't make any kind of sense at all. The Z transform is a thing that exists only on sampled functions, right? Like it doesn't make any sense otherwise. Now, another thing that's a bit confusing is that you'll see that from a mathematical point of view, all of these notations imply that there used to be a continuous function. Mostly because that's the kind of applications that we use it for. But it is also completely possible, right? If I just have a table like this, so if I just have a table like this, which defines a discrete function using the values at the times, right? So if I just had that table, let's say I had exactly that table, 0.9, but let's say for convenience, you'll see why it's convenient now. Let's say for convenience we're doing something like this, where the signal started out as 0 and ends up at 0. And is only non-zero for a finite number of spaces in between. So exactly for these 3 points that I've got on the board there, right? I could write down the Z transform of that sampled signal using only that spreadsheet. Okay? And in fact, you wouldn't have to tell me any story about what used to be the function. In other words, if you just said, here's a spreadsheet of values, it's got 3 non-zero values, you calculate you calculate the Z transform, you would simply say, well, that is equal to y of Z is equal to 0.4 times Z minus 1, and you'll hear me, trust me, this Z thing is like, it's a lot of trouble when you're talking. You know, you hear me say Z minus 1, Z minus 2, Z minus 3. What I really mean, obviously, is Z raised to the power of minus 1, Z raised to the power of minus 2, and so on. We favor these negative powers when we're doing math, mostly because we like that causal form. And so because remember, that Z is defined effectively as a forward step in time, like a forward shift in time. We like backward shift in time for reasons that we've discussed at length already. We like being causal when we write things, and so we prefer having things that goes Z minus 1. But so what I'm doing here is I'm writing down the Z transform of that value, 0.83 times Z to the minus 2 plus 0.9 Z to minus 3, full stop, right? So what I've done here is I've just taken the list of values that you gave me, or that we started with. I've written them down as a polynomial in Z, and that is the Z transform of that sampled signal. Okay? And so I want you to understand the basic mechanics here, right? The basic mechanics, forget about the interesting math. If you look on any other source where people talk about Z transforms, the only thing that they really care about is this relationship. It's the idea that as I take these signals, every row of this spreadsheet corresponds with an entry in the polynomial, right? So if I have a finite signal, if I have a finite length signal, what that means is if I have only a small number of values that are non-zero, I don't need any magic at all. I just take the values, I put them as the coefficients of the appropriately raised Z. And that's the whole story. And so this allows me to encode really, really straightforwardly any kind of signal that is just this kind of what they call finite support. In other words, that is non-zero over a kind of a finite range of values. And so if we only had finite signals, that would be the only thing that we ever needed to do, right? We would forget about all of this, all of these definitions, we'd forget about the math and focus on the operational definition, which is you look at the values of the function at the sampling points, and you use those values as the coefficients of this polynomial in Z. Okay? And if we only had small signals, that would be perfectly fine. The problem is, I work up a huge sweat when I'm writing down infinite series, right? It doesn't leave me a lot of time for the other questions in the exam if I'm writing down an infinite number of terms. And so I'm looking for a way of saving effort, okay? And so when does this other kind of thing arise? And I want you to understand, this is not a different thing. It's not even actually operationally different. It's a mathematical trick that stops you from having to write down infinite series, okay? Because let's imagine that I'm trying to do this exact same thing, and I want you to understand that this operational example that I've given here is perfectly compatible with the definition in the box over here, right? It's literally what that definition in the box says. You take n equals 0, and you take the 0th version of f of t, right? Let's rather say include the box over there. You take the 0th term and you multiply it by n to the power minus 0, which is 1. And that's like the constant term. And then you take the first term and you multiply that, the first value, and you multiply that by z to the minus 1, and so on. And you just keep going, okay? So what if f doesn't have a finite number of terms? What if it has an infinite number of terms? And we come across this a lot because maybe we come across a function that looks a little bit like this. Now, I'm just going to be funny and say, let's say that function, well, let's first do this one, which starts at 0 and goes up to 1. And how would I get the Z transform of that signal? And I want you to first understand that what I'm doing here is I'm just getting effectively a fancy Laplace transform, right? I'm getting a fancy Laplace transform if I look through the sampler with my little bit of math. But operationally, I know that if this is f of t, then f of z will be equal to 1 plus 1 times z to the minus 1 plus 1 times z to the minus 2, and so on. And I'm just going to like elide that. But it's implied that this is an infinite sum. And now I'm going to do something which is not at all part of the definition of the Z transform. I'm simply going to notice that I know formulae that enable me to simplify infinite sums. In this particular case, I'm going to notice, well, in fact, let me show you. You don't even have to notice this. You can actually rely on SymPy to do this. Because SymPy is amazing. It's unfortunately not as amazing as we would like it to be. And this is again one of the places where we kind of break down. Now remember that we've already defined this is kind of the prelude that I've already spoken about. So this is what I regard to be the definition of the Z transform in this particular case, right? So we just have this, I've used K instead of N. And again, this is really amazing. SymPy has, firstly, straight up notation that allows us to express this infinite sum. So you can see here, I've simply taken here, I've taken the unit step. I've said that is exactly this thing that I've just expressed here. I suppose you could probably, if you want to make it closer to what I had in the, if you want to have it really close to what I had in the book, that's exactly what I had in the book, right? So you can do that, okay? So does everybody see that that's basically the same as this, right? So we've taken a unit step, we've sampled it at the points. For a unit step, all the points are 1, right? Like it's 1 everywhere except for negative values of time. And that's what that infinite sum looks like in SymPy. And you may be surprised that when I construct this object, now please notice there's a SymPy.sum with a small s, and there's a SymPy.sum with a big S. So just be aware that this is with the big S, and so that's actually building a sum object. It's not actually doing anything. That's why I can display it like that. And then to actually do the thing, that object has this method called doIt. There's the same idea. There's the same idea. You can build an integral like the same way. So you can kind of build an object that represents that integral before you actually do the integral. And again, to do it, you would use doIt. Okay? But there you have it. It's a little bit small there, but let me try and zoom in a bit. So there you have now what that form is. What SymPy is telling us is, okay, under certain convergence conditions, right? SymPy is cleverer than most of us and looks at that series and is like, hey, that looks like a geometric series. Does everybody notice that that's a geometric series? Does everybody remember what a geometric series is? So a geometric series is this, in Afrikaans, it may be a little bit more familiar if I say rye en reekse, right? So this is a geometric series, in other words, a meetkundige reeks, right? And what that means is that I am taking every term of that sum and I am multiplying it by a constant factor. The constant factor in this case is z to the power minus 1. And so I start at 1 and then I multiply that 1 with z to the minus 1, and what do I get? 1 times z to the minus 1. If I take that term and I multiply it again by z to the minus 1, I end up with z to the minus 2. And so on and so on and so on into infinity. And you guys remember that under certain conditions, these series will converge. And if the series converges, SymPy knows that this is the formula for that infinite sum. And so I want you in your mind to be incredibly clear on when the Z transform stopped here. Because people get super confused. They imagine that this thing is the operation of the Z transform, because that is something that looks a lot like the kinds of things that we wrote down when we wrote down Laplace transforms. And yes, it is super useful that these infinite series have these finite representations, but I want you to understand that that's not me doing the Z transform, that's me taking an infinite series and writing it as a short sum. Okay? The Z transform definition got me only up to there. And my knowledge of geometric series got me from there to there. Now, I will not expect you, either in the exam or even in next semester's work, ever to intuit purely from a geometric series what that short form would be. Unless there's an easy way to get from the one place to another. I'll show you an example of like what this easy way of getting from one place to another would be. But I don't expect you to be able to, what I'm actually saying is I don't expect you to be able to derive the properties or the entries that I give you in the datasheet table. I expect you to use them and be aware that they exist. Okay? And so in the same thing of being aware that they exist, so just to finish my thought over here. So you can see I'm using equal signs all the way through there. Right? This is not a weird approximation. This is not something that is like, well, you know, like some clever guy got this amazing approximation. This is simply the fact that these infinite series within the region of convergence are literally equal to that. And so you will find that if you look at the data sheet, you will find a whole lot of different functions of time, right? That's f of t, and then you will find kind of the z transform of f star of delta t. That is what is captured in the table, are kind of these short forms, and it's not always a geometric series. You know, like just like with the Laplace transform, I don't know if you remember or if you ever just maybe for curiosity's sake went and looked at some of the derivations of the Laplace transforms. I mean, that's some deep mathematical stuff going on there, right? And I don't expect you to be able to kind of pick up on those things. I do expect you to understand that these infinite series have this finite representation, and that is incredibly useful. I also expect you to understand that downstream from this, almost all of the problems that we'll encounter when we are doing things with these series are just manipulation of these rational functions of z, in the same way that many of the problems that we were encountering in Laplace are just manipulations of rational functions of s. Okay, so because now, once we are here, once we have this way of writing the mathematical equivalent, all the things you know about the Laplace transform, you also know about the z transform, because the z transform is a Laplace transform, right? So the z transform is also additive and associative, and it's also a linear transform. It's all the things that you know about the Laplace transform. Why? Because it is a Laplace transform. The only difference is that we've introduced this little bit of additional utility. So we've introduced this thing called z to make the notation easier so we don't write. The other thing that is a little bit unique about the sample domain idea is that that it involves sums of these infinite series instead of integrals, pretty much. Or let's rather say that the signals will always contain these sums, where the signals that we were using with Laplace, if we just did like the Laplace transform of a unit step or whatever, that didn't look like a sum at all, right? But it looks like a sum by the time we write it in the Z transform. Yes?
So why would we need to do this in discrete systems? So we can solve like differential equations, because that's kind of what we use Laplace for.
Well, remember we did a lot more than just solve differential equations, right? We did this whole school of analysis where we said that because, so we're going to kind of recapitulate in these 2 weeks, or this little bit of what's remaining in this week and next week. We're going to say, what is the discrete equivalent of the Laplace transform of a signal? And then I'm going to ask tomorrow, I'm going to ask, what is the discrete equivalent of a transfer function? Because remember, we've encountered the Laplace transform in 2 very different modes. One where we were thinking that we were just operating on functions of time, and one where we were thinking that we were operating on system equations. And the mindset for that was very different, but I want to remind you that the output was exactly the same, right? So we are used to this idea, you should be used to this idea by now, that I've got a function of time, and I've got a machine that operates on it, and then, well, let's call that u. You know, I've got a function of time, and I've got a machine that operates on it, and then I've got this other thing that comes out. And you're used to the idea, well, I'm going to do the Laplace of this thing, I'm going to do the Laplace of this thing, and like what goes in there is like dx dt is equal to whatever, right? That's the function definition, that's the equations describing the system. While what goes in here is something that looks like a function over time, right? And those are very different things, but remember that by the time we did things, we had things here, right? That's a possible version of this game, right? I could take the Laplace transform of the unit step function and end up with 1 over s, and I could tell you that this is an integrating system, and that transfer is also 1 over s, right? And so these very different ways of thinking about the world led us to exactly the same math. And by the time we got there, they were indistinguishable, right? We couldn't say, oh yes, I know that one came from a system description, and that one came from a signal description. Because this is a good proof of that, because they're the same thing. And so we couldn't work backwards just with that knowledge. If I just wrote down 1 over s, you couldn't tell me whether that represents a transfer function or a signal, okay? Then we got to this point, and we would end up with y of s, and then to get to time, we would do the inverse, right? And we're trying to figure out, can we use the same tools, all these powerful tools that seem to do really well on analyzing systems in the continuous domain, are there discrete equivalents of those? And I'm moving from left to right on this graph, right? I've just showed you how to get the discrete version of a signal.